Hello everyone. So far we have seen many topics of linear control theory, and especially the stabilization concepts and controllability observability, followed by its usage for control design, and we also saw observer design as well actually. So, we will proceed to a very kind of different concept now, where we tell control theory, I mean control design can also be done from optimization perspective, and that is where we need to have some optimal control coming up and all that. But before that, we need to have some appreciation of what is called a static optimization or parameter optimization, followed by I will take you through some overview of calculus of variation as well, and then based on those things we will be able to synthesize optimal controllers, and especially this particular course will primarily concentrate on linear control theory, even though we will talk a little bit on nonlinear control as well. So, let us proceed further with this particular lecture, where I will talk about static optimization, or some books it is also called as parameter optimization, where things are not changing with respect to time, it is all stationary, and with respect to a stationary objective we are going to minimize or maximize certain objective function actually. So, the topics will be like this. First is unconstrained optimization. So, if there is no constraint acting on the optimization, then what are the standard results? Then we will talk about constrained optimization with some sort of equality constraint, and then we will see something overview on inequality constraint as well, and on the way we will see lot of numerical examples actually. So, let us start with unconstrained optimization. What we are telling here is let us concentrate on the curve that is J1 with a scalar x actually. So, I will start with a very simple thing, where the objective function is a function of only one variable x, and we are analyzing this function J1, okay, this particular function J1, and we want to answer this question where all its local minimum or maximum exist actually. And without going through too much of math, we can observe that this point 1, 2, 3, 4 are kind of possible candidates that we are bothered about actually. Okay. And even without analyzing too much of math, we can also clearly say that point 1 is a local maximum, point 4 is a local maximum, point 3 is a local minimum, point 2, well, we cannot say too much of things right now, but it looks like a candidate for either minimum or maximum, or what is mathematically called as point of inflection actually. Okay. Anyway, so and the common thing that we are worried about is we just observe everywhere point 1, 2, 3, 4 is that everywhere the first derivative turns out to be 0. Everywhere if I take a slope here at point 1, point 2, point 3 or point 4 local slopes, the slopes are all 0 actually. Okay. So, it kind of gives us an idea that very possibly whether it is minimum or maximum problem, the necessary condition turns out to be like first derivative equal to 0, and that we have to see little formally. This is just an observation at this point of time. Okay. Now, coming back to the cost function, this curve J2, suppose instead of J1 I have J2, and I want to see the difference between J and J2. Suppose I have J2 instead of J1, then it turns out that I have only one minimum actually, and because I have only one minimum between x and xb, whatever answer I get, even though I use only local conditions, that is going to be global as well, because I have only one solution anyway. Okay. Now, coming but that is same thing cannot be said about J1, because suppose you have point 1 and point 4 both are local maximums, but point 4 will be kind of a global maximum within this domain basically. But this particular lecture and this particular course will not worry so much on global minimization or maximization. We are all interested in local conditions, and we also concentrate mainly on necessary conditions, not sufficiency though. Okay. So, let us see this analysis little formally. Okay. So, what you are interested in, we want to have a performance index, that is our objective for minimization or maximization, depending on the problem we have to select one. and then we are interested in analyzing this function at x star. Okay. That means j of x star plus delta x minus j of x star, that is using Taylor series, I can write it that way. Okay. And also remember that Taylor series satisfies a nice convergence condition where it turns out that the first term is most dominant, the second most dominant compared to rest of the terms, and after the first term goes, the next term becomes most dominant compared to rest of the terms, like that actually. So, if I take this minus that, then it turns out to be the series is like that, and what I am interested in by either minimum or maximum is that this function that I am looking at, j of x star plus delta x minus j of x star, that is the difference between the two values of the function in the neighborhood of x star. This quantity has to be sign independent of delta x. That means, either I go to negative side or I go to this, let us say point 1, then either I go to negative, I mean left side of point 1 or right side of point 1, the function value has to decrease actually. That means, the result that I am looking is it has to be either greater than 1, I mean greater than 0 or less than 0, irrespective of sin delta x actually. Okay. But I cannot say that as long as this term is non-zero, okay, because delta x is a sign sensitive term, it is a linear term. So, to make this left hand side quantity sign insensitive, I must necessarily have the first derivative equal to 0. Okay. So, that will make sure that j of x star is either minimum or maximum irrespective of the sign of delta x actually. Okay. So, that means this necessary condition turns out to be that this is equal to 0. Remember, this particular term is dominant compared to rest of the series actually. So, that is the reason why we want to make that this first term equal to 0 actually. Okay. So, that turns out to be necessary condition. What about sufficiency condition? Okay. So, after this has become 0, then the series is series starts from there, this left hand side. So, let us see that left hand side we are left out with that, where this first term is a quadratic term now, and if it is quadratic, obviously it is sign insensitive already. Okay. And then if we just have this condition, that means this second derivative turns out to be greater than 0, then this left hand side is certainly greater than 0 actually. Okay. So, that will make sure that this quantity is greater than that quantity. Okay. J of x star plus delta x is always greater than j of x star, no matter whatever is the sign of delta x. So, that means this gives me a sufficiency condition that second derivative has to be greater than 0 for minimum and second derivative has to be less than 0 for local maximum actually. Now, the question is, okay, if it happens that you got the first derivative equal to 0 and the second derivative happens to be either of that, then we are done anyway. What about the second derivative also equal to 0? Then this term is also not there. Now, in that situation, okay, you have to analyze the third term, and the third term means this particular term here. Again, this has become sign sensitive because delta x cube actually. So, because it is sign sensitive now, so we have to have another necessary condition which should tell that the coefficient must be 0. If it is non-zero, then it is certainly a point of inflection and we are kind of done actually. Okay. But if the hope is still alive, that means the x star value is still either a maximum or minimum, then another necessary condition has to be the third derivative has to be equal to 0, and again the following sufficiency condition will rely on the fourth derivative this time. Okay. And this analysis continues that way, right. So, I mean the idea here is, suppose you want to get a minimum or maximum, then first thing you apply a necessary condition, get the solution for that x star values will pop up from there, and for various x star values you check this condition, okay, the second derivative condition. If it is either strictly greater than 0 or strictly less than 0, we are done. Okay. Otherwise, if it is equal to 0, then you continue with the third term and then make sure, I mean just observe that this is also equal to 0. If it is not 0, then it is a point of inflection, and if it is 0, you go to the fourth order term and make sure that it is strictly greater than 0 or strictly less than 0. If it is strictly greater than 0, it is minimized, x star is a minimum point, and if it is strictly greater than 0, then x star is a maximum point actually. Okay. Alright. So, these conditions will rely on these odd powers of this derivative and all that, odd derivatives and even derivatives essentially. So, we will see some example very quickly. Suppose j is like x fourth, then the first derivative is tells us that this is 4x cube, which is equal to 0, and hence x star solution turns out to be all zeros actually. So, you take the second derivative, it is also 0. So, we cannot say anything about it right now. We will proceed with the third derivative, which is again 0 at x star, that is more important. So, we will go to fourth derivative. In fourth derivative turns out to be strictly positive, and hence it is x star value, which is 0 0 0, is certainly a minimum point actually. And it is very clear from the picture also, like if you just simply draw this picture, like this x versus x fourth, then the curve will turn out to be like this actually. This is x fourth curve actually. Okay. So, obviously, if okay. So, obviously, this has a minimum point at x equal to 0 actually. Okay. So, that is what graphically it means, and this is what we analytically we can get actually. Now, let us change the objective function little bit, and you tell okay j equal to x cube, then what actually? We proceed with the same analysis. Again we have only 2 solutions here, not 3, all are same by the way. But then second derivative turns out to be 0, however, the third derivative is not equal to 0, and hence it is a point of inflection. Again if you want to draw the curve, I mean then this is something like that will happen. Okay. This is x versus x cube, then obviously this point is has a point of inflection. The slope is 0 here at 0 point, but after that this it go, I mean on the right hand side it increases, left hand side it decreases actually. Okay. So, that way it is a point of inflection actually. Okay. All right. So, these are all about scalar case. Now, what about vector problem? Those are more practically relevant, because the objective function, even though it is a scalar, the variable that it takes can be more than one, and that is more realistic actually, because normally your objective of a minimization maximization will typically act on several free variables actually. So, if you take various combinations of those variables, then you will get some sort of a minimum maximum actually. So, how do you handle this case? The analysis is fairly similar to what we have done, but here by definition we have to have this Jacobian of J and Hessian of J matrix actually. The Hessian matrix will pop out that way, Jacobian is like that, and then the Taylor series idea will stay as it is. We apply the Taylor series of J of x with at x star, and then we analyze this Taylor series turns out to be that way. We notice that this is actually a okay. All right. So, this turns out to be like okay, maybe there is a transpose out there, because of this like vector matrix notation compatibility has to happen actually. Okay. So, then okay. So, then the second term like that, and third term onwards is a little bit more complex. So, we will not worry so much on that actually. So, if you take this one minus that term, again this first term onwards it will pop up actually, and also remember now the function value, the difference that you are looking at from this term minus that term has to be sign insensitive irrespective of whatever delta x components sign actually. Delta x will contain several components, and no matter whatever the sign of each of these components, whether positive or negative, we must have this sign insensitive thing actually. Okay. So, obviously I mean that means geometrically speaking, no matter which direction you want to travel, your function has to either increase in all direction or it has to decrease in all directions actually. So, necessary condition from this analysis, obviously we want to have this first term 0. That means the gradient vector that you are talking, or the Jacobian thing that you are talking for J has to be 0 actually. So, this is del J by del x is a gradient vector now evaluated at x star has to be 0, and the sufficiency condition will be dictated by that, which tells that okay, this entire quantity needs to be positive actually. That means by definition something like suppose we take tell that x transpose A x, if you remember matrix theory sort of thing little bit, and then if this is strictly greater than 0 for all x not equal to 0, okay, then A matrix is actually PDF actually. This A matrix is a positive definite matrix. Okay. This is a positive definite matrix. Okay. So, symbolically we write that as A is greater than 0 that way. So, that is that means coming back to this this idea that this quantity has to be strictly positive all the time, then this matrix has to be positive definite actually. So, for sufficiency, I mean for necessary condition of either maximum or minimum, this first derivative has to be 0, which is a gradient vector now, and the sufficiency condition tells for minimization this particular matrix evaluated at x star, that means it is a pure number now, it has to be positive definite actually. So, the procedure remains almost similar to what we have done. First, we will equate these equations, and remember this will turn out n equations, because right this is like a n dimensional vector now. So, this is a vector equation actually. So, we will have n equations and n variables from, because x is a multidimensional variable now. So, if you have n equations and n variables to solve for, once you solve it you will get x star, and at x star you can evaluate this and tell if it is positive definite, then this is certainly a local minimum point, and further conditions are difficult. So, we will probably try to skip it in this review lecture actually. Okay. Now, coming back to an example, j of x is let us say half of x 1 square plus x 2 square. Then the necessary condition, as I told, the first gradient, first you take gradient vector and make it equal to 0. So, del j by del x 1 is turns out to be like just x 1, del j of del x 2 turns out to be x 2, evaluated at x star value. So, that means x 2 star now, with both has to be equal to 0 0. This is a direct solution now, because these are no more equations. But if it is equation, then also you can solve it, because we have number of equations are equal to number of variables actually. In this case, we got a direct solution, a 0 0 origin is turns out to be a candidate solution. Now, let us see whether this candidate solution satisfies sufficiency conditions as well. So, sufficiency condition tells us that this matrix I have to evaluate at x star, and in this case it turns out to be just an identity matrix, it is independent of x star actually. Okay. So, identity matrix eigenvalues are obviously 1 1, it is a diagonal matrix 1 1 actually, so both are positive, and hence this matrix is positive definite. So, this that means this second I mean this Jacobian matrix evaluated at x star is positive definite, and hence the x star candidate solution that we got from here has to be a minimum point solution actually. Okay. So, that is how we proceed with that actually. Now, suppose you change this problem again a little bit, and we take a different problem now. So, let us say instead of x 1 square plus x 2 square, okay, we just change the problem to x 1 square minus x 2 square, then what happens? We will again start with the same idea, we will just take first derivative, and that will give us that x star candidate solution. Again it turns out to be 0 0. However, when you take second derivative, the eigenvalues turns out to be 1 positive and 1 negative, and hence it is neither positive definite nor negative definite. Okay. And hence it turns out to be a saddle point actually. In other words, one side the function gets a minimum value, and the other side it turns out to the function gets a maximum value actually. Okay. And these are typical textbook examples will be like horseback sort of thing actually. Okay. So, one side it will be going positive, I mean function is increasing, other side is decreasing basically. So, pictorially speaking, if you take a picture that way, then it is let us say x 1 is this way, x 2 is this way, okay, x 1 is this way, and you have a j that way. Okay. Then this function is somewhat like this. Okay. So, this is a 0 solution, no matter whichever direction you want to go, you will get a solution which is minimum at 0 0 actually. Okay. Now, the same thing cannot be said for this will have something like a one side, I mean I do not know whether I will be able to draw a picture correctly, but let me try. Okay. So, this will be like one side it is minimum, but the other side if you see it is something like it will happen that way actually. Okay. Okay. One side it is going to increase, okay, one side, but the other side is going to decrease actually. Okay. So, that way I mean this may not be a very correct picture to visualize what is going on, but you can see the horseback whatever people put, one side it is like this, okay, the other side is like that. Okay. So, those are the type of things what we call as saddle point actually. It is a multidimensional thing, it is not no more called as a point of inflection, it is called saddle point actually. Anyway, so those are all free optimization both in scalar as well as multidimensional case. Now, the free optimization is also not very relevant in practice. In practice, we have to optimize certain cost function subject to certain constraint equation actually. And constraint equations, if it exists, then how do you kind of handle those actually. Okay. So, first thing we will talk about equality constraints, then we will move on to what happens when there is inequality constraints actually. Okay. And these are all in multidimensional case now actually. So, our objective is something like this, we want to minimize, okay, without the loss of generality we will talk now minimization only. Maximization will be part of the deal, just that you have to take care of the conditions appropriately actually. So, we want to minimize a objective function, and then when you talk about optimization problems, typically the cost function turns out to be always scalar, okay, unless you talk about multi-objective optimization, that is a different subject altogether. But normally the objective function or the cost function is a scalar quantity, but the variable that it takes can be multidimensional actually. Okay. So, we want to minimize this cost function, okay, subject to this equality constraint, okay, and this equality constraint need not be one constraint, it can have several constraints actually, like f1 of x is to 0, f2 of x is 0, like that up to fm of x is 0. That means, the number of variables are n, but the number of equations are m, they need not be same either basically. Okay. So, you see that this is a m dimensional constraint where the n dimensional free variable, but the objective function is a scalar quantity actually. Now, how do you solve it? Whatever solution we intend to get, it has to certainly satisfy this constraint first. If it does not satisfy the constraint, we are not interested, that is not the right solution either basically. Okay. So, how do you do that? It comes from a great theorem that Lagrange proposed, is a great mathematician, that this problem can be equivalently solved by putting, by formulating an augmented cost function in terms of lambda, okay, where that is defined as like that. Theoretically speaking, lambda transpose f of x, remember f of x is equal to 0. So, that is kind of 0 actually. Okay. But you consider that restriction for a second and concentrate on this augmented cost function, where lambda is a free variable, let us say. Okay. That means, if lambda takes an appropriate value in the process of optimizing j bar actually. So, we just consider this j bar as a free optimization problem, where we have to deal with this extra variables lambda, and remember this lambda is same dimension as f, because ultimately this is a scalar. That means, you have m such lambdas, lambda 1, lambda 2 up to m actually, lambda m basically. So, we have j bar, which is j of x plus this lambda transpose f of x, where x and lambda both act as free variables actually. That is the whole idea there. So, how do you do that? Now, necessary condition turns out to be one with respect to x and another with respect to lambda actually. So, if you take derivative with respect to x, then this is del j by del x plus lambda transpose del f by del x. Otherwise, you can also write that way actually. Lambda c is, remember, as long as the multiplication is a scalar quantity, okay, we can have x transpose y is y transpose x also, as long as this is a scalar quantity basically. Okay. Okay. So, similarly, you can alter the sequence of derivative here, but you can, if you want, you can keep it also basically. Altering it helps us in solving the lambda actually. So, we will just take an alternative way and tell, okay, this del j bar by del x is like this, del j by del x first plus this one del f by del x transpose times lambda actually. So, this will give us n equation, remember that this is a scalar and this is a vector. So, del j bar by del x is a vector quantity, it is a vector equation which will give us n such equations actually. Okay. And how about del j bar by del lambda, because that is also a free variable, we have to take derivative with respect to that also. Remember, this does not contain lambda, so this is gone, and this is only simply lambda, lambda appears linearly here basically. So, the answer to that is simply f of x actually. So, that this second condition turns out to be f of x equal to 0, and that will give us m equation, and this f of x equal to 0 means the same constraint equation actually. Okay. So, as part of the necessary condition that we want to satisfy for this pre-optimization problem, that necessary condition turns out to be the same constraint equation. That means, we are not violating the constraints actually. Okay. So, we want to solve these two equations, two set of equations together, where we have n equations coming from this and m equations coming from that. And how many variables? Obviously, we have x which is n dimension, n variables, and lambda which is m dimension, which is m variables. That means, we have n plus m equations with n plus m variables actually. So, obviously, we can solve this. And once you solve this, you get a solution for x and lambda, where we are not typically interested in the lambda variable solution. We are interested in only the x variable solution actually, but lambda helps us in getting the solution. That is the tricky thing actually. Okay. Now, let us take an example again. We will go back to the same example, where we earlier got 0 0 as the solution. Now, we want to examine the same cost function. We want to minimize that subjected to this constraint equation now. Remember, this is a kind of a plane equation actually, x 1 plus x 2 equal to 2 basically. So, this cost function that we had earlier, okay, this subjective function, the solution is no more at 0 0, remember that, because we are interested in analyzing some sort of equality constraint with respect to a plane now actually. That means, wherever this plane cuts this objective function, okay, on that boundary surface we will get some sort of ellipse, and then on that ellipse we are interested in wherever this minimum maximum happens actually. So, we are not bothered anywhere else actually, we are only bothered about that particular ellipse actually. Okay. So, obviously, the 0 0 is no more a solution candidate actually here, in just by intuition. But let us see whether we get that answer or not actually. Okay. So, by procedure we formulate an augmented cost function like this. So, that means, this is what it is, this j plus lambda times this entire equation equal to 0. Remember, if it is given like equal to 2, then you take it, make it minus 2, then make it equal to 0, then augment here actually. Okay. So, we have only one constraint equation, so only one lambda basically. So, the solution turns out to be the necessary condition. We have to apply the same thing with respect to x 1, with respect to x 2, and with respect to lambda as well actually. So, if we do that, then with respect to x 1 it is like this, with respect to x 2 is like this, and with respect to lambda is the same constraint equation again basically. So, we got three variables, x 1 star, x 2 star, and lambda star. And obviously, if you sit down with the solution, then x 1 star is minus lambda star, x 2 star is minus lambda star. By the way, all the star notations are some books they follow this, they tell it is the optimum solution actually. Okay. So, when you see a star, that means it is a optimal solution value basically that way. So, we have this x 1 star and x 2 star is minus lambda star, both are same, and then you substitute back it here, we will get that lambda star minus 2 lambda star minus 2 equal to 0, that means lambda star is minus 1, and hence minus lambda star is plus 1. So, you get x 1 star, x 2 star is 1 1 actually. Okay. So, obviously, somewhere here, okay, in the function somewhere here the minimum exists actually, that means the minimum will be somewhere here. Okay. If we take the projection basically. Now, if you just generalize that a little bit more, this is a specific case for quadratic cost function with linear constraints. By the way, this quadratic cost function and linear constraints are heavily studied in both static optimization and dynamic optimization, that is optimal control, primarily because you have this closed form solution ultimately actually. Ultimately, what you are getting is a nice closed form solution. And if you can formulate a quadratic cost function, if you can formulate your problem in terms of a quadratic cost function and linear constraint, then we should be very happy about that actually. Ultimately, the results turns out to be neat actually. Okay. So, to generalize that a little bit, you can take a little more general quadratic cost function in two variables, and then you can take a generic kind of a plane equation here, and then you can proceed with the same algorithm, and then finally get a solution which is very generic actually. Okay. Just by plugging various values of a, b, and m and c, you will get a general solution already basically. Okay. Also, a small remark that lambda star that you are ultimately getting has no physical meaning actually, it only helps to solve the problem. Okay. And that is true for optimal control also basically. Okay. Now, what about sufficiency condition for constraint optimization? then the sufficiency condition turns out to be that way. It is no more only this Hessian matrix actually. You have to formulate this equation, you take this minus I sigma and augment this, and you have to take this transpose here or here depending on whether you have single constraint or multiple constraint actually. Okay. And that will be very apparent from the dimension of what you are getting here actually. Ultimately this has to be a square matrix ultimately. Okay. So, once you put it there and then make a determinant equal to 0, you get a equation for sigma, and it is, if it has only positive roots, then it has a minimum problem. If it is all negative roots, it is a maximum problem actually, it is a maximization basically. So, that is the sufficiency condition for equality constraint problems actually. And you can actually go ahead and show that sufficiency condition also. So, for example, if you take the same quadratic cost function with a little different constraint equation, then you can proceed with the same idea, then you get okay, necessary conditions when you apply, it gives you that kind of a solution actually. Now, what about sufficiency? I have this second derivative turns out to be identity here. So, I will take a second derivative, but just because the second derivative eigenvalues are 1 1, I am not yet done, I have to do this and other thing actually. So, I take del f by del x turns out to be that way. So, I put it here, okay, and this is the transpose of that. So, I put it here, okay, and then ultimately I form the determinant, and then this the sigma solution turns out to be 1, which is certainly greater than 0. So, strictly positive. So, that means the solution is a minimum solution actually. Okay, that is what that little extra algebra you have to do. So, some remarks, what you had this in this example x1, x2 and lambda do not appear in the equation for sigma actually. Okay. What you get as equation for sigma is all constant numbers and only sigma there. That means, the solution that you are getting here is independent of x1, x2 and lambda, that necessary condition throws actually. And obviously, hence the solution is the only solution, we do not have this multiplicity and all that, and hence the result is global actually. Okay. However, in general, if you see this algebra, these will contain x and lambda somewhere, and then if you have those kind of situation, you will have multiple things and you have to answer for each of these cases actually separately. So, various conclusions have to be derived on a case to case basis actually. That is the remark that you should note actually. We will proceed with another example, where this we just change this subjective function and the quadratic constraint now. See, this constraint tells you that x1 square plus x2 square equal to 1 is nothing but a sphere in 2 dimension actually. I mean, if you take this is a 3 dimensional problem, x1 square plus x2 square equal to 1 gives us some sort of a, well, if you plot it in 2 dimension, because this is a constraint problem actually. So, in 2 dimension it is a circle basically, x1 square plus x2 square equal to 1 is a circle equation basically. So, you have to minimize or minimize this cost function subject to this circle equation actually, right. And many times the solution may not exist also, that is another problem actually. All throughout this lecture and probably throughout this course, we will assume that the solution exists and try to find a solution basically. Now, if your constraint equation does not intersect with the cost function, then obviously this solution does not exist actually. So, we will not talk too much on those existence issues and all that here. Anyway, so we will proceed with the solution approach. So, obviously, this j is j bar is j plus lambda times this one, again this is a single constraint equation. So, this part is j, this part is lambda times this, remember this is equal to 0, already it is given in that form. So, I put it there, and the necessary condition turns out to be these 3 again, and a sufficiency condition now is a function of lambda at least actually. Okay. I mean this and I mean the second derivative of j bar del square j bar by del x square turns out to be like that, and del f by del x is turns out to be like that, and things like that actually. Okay. Remember, this is j bar. So, j bar will throw you lambda x and all the x and lambda both actually. Okay. So, this is del square j bar by del x square, which is only lambdas, then del f by del x contains x1 and x2 also. So, we put it back together, and then the sigma equation that we are talking will contain, it is a closed form solution nonetheless, but the solution is a function of x1, x2 and lambda as well actually. So, you get various cases now, because this necessary condition is also nonlinear actually. Remember that this is like a quadratic equation, this is a multiplication term, and this also multiplication term. So, various possibilities it will throw, and these possibilities turns out to be like that, these 4 possibilities you will get, and then you have to get sigma values, that is the solution of this at those points if you evaluate that, then the value turns out to be like that. So, these two values are strictly negative and these two values are strictly positive actually. So, what you are telling here is this combination that you are getting 1 0 and that is certainly a local minimum maximum point, minus 1 0 is also a local maximum point and these two are local minimum point. Okay. And all these conditions necessary sufficiency are all local actually. So, if you really want to find out global maximum and global minimum out of this, then you have to see you have to evaluate the cost function on these two values, whatever solution you are getting here. You formulate one more column for the evaluation of cost function, evaluate the cost function and take the minimum of these, the maximum of these two will give you the global maximum and the minimum of these two will give you the global minimum actually. Or we are not so much interested in this global minimum maximum concept actually. But typically gradient solutions are not suitable for finding out global minimum maximum in a good way. Okay. But anyway, but the concepts are like that actually. So, if you really want global ideas, global answers, then evaluate the cost function as various points and compare these two maximum points or multiple maximum points, then find out which is the most maximum value there, then that becomes global maximum and similarly for global minimum actually. Now, what about constraint optimization with inequality constraint? These are all with equality constraint actually, and inequality constraints are nicer also in a way, and they are also even actually real life problems will be partly constraint, all constraint optimization problem where the constraint equations will be partly equality and partly inequality actually. So, let us see how do you handle these inequality constraints actually. One primitive idea is like this. Suppose your cost function is a function of several xi's and each of these xi's are bounded between these minimum maximum values. Okay. Typically, this if you see control design problem, then each of these control variables will be bounded between certain minimum maximum values actually. Okay. If you are interested only in satisfying the inequality constraints of the control variable. So, what is the idea? Idea is, let us say I will replace this variable, okay, by another variable alpha I, which I tie up with this that way. This is the equation that I will formulate for xi, and wherever xi is appearing in my objective function constraint equation everywhere, I will replace this that xi with this values, this equation, and then consider alpha I as a free variable actually. Okay. So, I will solve this for alpha I and then I got a solution for xi. And what is the idea here? If I formulate this equation, this remember sin square alpha I can take values between 0 and 1, and if it is 0, then obviously xi will get a minimum value, if it is 1, it will get a maximum value. Okay. And anywhere in between it will be a kind of an intermediate value actually. Okay. So, the whole idea is to replace xi with this equation and then consider alpha I as a free variable actually. But unfortunately, this approach does not work very well. And then so many times this sin square alpha I, that solution that you are getting for alpha I must satisfy sin square alpha I should be bounded between 0 and 1. It kind of falls apart actually. Then if it is there, then you will not get a solution for alpha I, and hence you are not getting a real solution basically, and that is not nice actually. And on top of that, if you do not have this free variable individually constrained that way, that means there are equation sense they will be constrained and things like that, then this approach will not hold good either, because individually component sense they have to be bounded between minimum and maximum value, then only you can apply this actually. Okay. So, what are the other idea then? So, let us talk about a little formal way that we are interested in minimizing or maximizing this scalar cost function, where again the variables are n dimensional with this m dimensional constraint equation which are less than equal to 0 0 0 now, okay, and then equivalently you can talk about greater than equal to also actually. Okay. So, we are interested in this inequality constraint equations and then tell how do we handle this kind of thing actually. Okay. So, the idea here is we will introduce what is called as slack variables. Remember, these are not equal to 0 basically, they are strictly less than 0. So, if I consider certain positive quantities, okay, mu 1 square, mu 2 square up to mu m square, and simply add them to those equations, then I can write it as equal to thing actually, equal to 0 0 0. That means this inequality constraint will be able to convert to equivalent equality constraints by introducing the slack variables actually. Okay. Then once you are there, then you can follow the routine procedure for equality constraint, but the thing is we have to have some solution for mu 1 to mu m, And remember this less than equal to 0, we do not know how far they are away from 0, that is another thing actually. And we want and hence we not want the conditions appearing in terms of mu's actually, because mu's are really unknown quantities actually. So, ultimately the conditions that we want to get should be independent of this mu 1 mu 2 up to mu m actually. So, can we do that? So, let us proceed with this. We now have a equality constraint, we have a cost function to minimize. So, we know how to do it anyway. So, we formulate this j bar, which is a function of x, lambda and mu also, because mu is also a free variable here actually. So, we put it together, okay, and then we use this lambdas actually. This is the summation sign is written as an alternative thing for vector matrix notation sort of thing. You can also essentially write lambda transpose all these vector equation actually if you want to, but this is more elaborately written in terms of summation sign. So, what do you do? Necessary condition turns out to be like this set of equation has to be satisfied. You have n equations coming up from x variable x1 x2 up to xn, then m equations coming from lambda variable, and one more set of m equations coming from mu variable actually. Remember, mu and lambda has to be same, there is the same number of slug variables and same number of constraint equations. So, that way the dimension of mu and lambda will be same actually. Okay. So, you put them and then they analyze this term by term, this gradient and turns out to be like that, and this one turns out to be the same constraint equation again, okay, the equality constraint sense, and the third one turns out to be 2 lambda j mu j equal to 0, because this is apparent from here actually. Okay. If I take del j bar by del mu, then only term is here, and that will turn out to be 2 times lambda j mu j equal to 0 here actually. Okay. So, I have to use these equations to get some sort of a condition that should be preferably independent of mu actually, the mu values you do not know anyway. So, let us analyze the equation a little bit. So, del j bar by del lambda j, this equation if you take, okay, and then tell okay g j of this one I will take the right hand side, and the g j of x is minus of mu j square, and suppose I multiply g j with respect to lambda j this time, and I will also multiply it with respect to lambda j that side actually. Okay. So, then I have this now the next third condition I will apply, and third condition tells me that lambda j mu j is equal to 0. So, if I apply that, then this turns out to be equal to 0 anyway. Okay. So, if this turns out to be 0, then what it tells me that lambda j g j should also be equal to 0 actually. Okay. So, this leads to the conclusion that either lambda j is 0, okay, or g j is 0, because lambda j g j is 0, right. Okay. So, that means either lambda j is 0 or j j is 0 actually. Okay. What does it tell you? That means, if the constraint is strictly an inequality constraint, then the problem can be solved without considering it, otherwise the problem can be solved by considering as a equality constraint. It means either the constraint is active, that is it is like a boundary sort of idea, it is active means it is satisfied in the equality sense, or it is inactive. If it is inactive, we do not need to consider that. If it is active, we need to consider that as an equality constraint basically. That is what it tells here actually. Okay. So, what is the solution approach now? We go ahead and do this, okay. So far we have used these two equations in this analysis. What about this? This one we have not used, so we have to certainly use this actually. So, the procedure tells us that okay, you formulate this set of equation and equations, and now you consider this set of equation lambda j g j, which is m such equations actually, and this one contains only lambda. Remember, mu is no more required actually. Okay, mu is no more there here. Okay. Even though we started like that, we are just concentrating on that part of the thing actually. Okay. All right. So, and then you carry on with this analysis, and I will kind of try to skip a little, and then it tell okay, j of x needs to be minimum if these two conditions, either of the two happens actually. That means, if g j is less than equal to 0, then lambda j has to be greater than equal to 0, or vice versa. That means, g j and lambda j must have opposite signs actually, okay, and for maximum they should have same sign basically. So, you have to get a multiple set of solutions from here, and then for each of that you have to say whether all these all these things happens. That means, if g j is less than equal to 0, then lambda j has to be 0 for all j's basically. Remember, j is like 1 to m actually. Okay. and then similarly for maximum actually. So, these are all what is called as Kuhn-Tucker conditions actually. So, these Kuhn-Tucker conditions are very neat, because ultimately it gives you a very precise test condition to check actually. So, some comments that one should explore all possibilities in the Kuhn-Tucker conditions to arrive at appropriate conclusions, and also remember that Kuhn-Tucker conditions that we are doing it is all derived based on these necessary conditions. So, certainly the Kuhn-Tucker conditions are only necessary. Now, sufficiency checks are also available, which also requires the concept of what is called convexity of a function actually. So, what is it? Function is either concave or convex provided certain conditions hold good, and if it is something like this, it is a strictly convex function. If it is something like this, it is a concave function. The whole idea is if the function is convex, if you draw a straight line between any two points, okay, then the straight line should lie strictly above the curve actually. Okay. If I take any two points here, I just join them together, okay, then the line lies above this curve actually, and it in this case the line will lie below this curve actually anyway. Okay. So, if the line is strictly above the surface all the time, then it is strictly convex, and strictly below, then it is strictly concave actually. So, how does it this convexity concavity useful in optimization, and the result turns out to be like that. So, I will result we will see here, but before that that how do you check it, because this is simply a concept actually. Okay. So, for evaluating, for getting an answer that the function is either strictly convex or strictly concave at a particular value of x star, we have the concept of this positive definiteness, negative definiteness again comes. So, if it tells okay, we can always evaluate this Hessian matrix and evaluate at x star value, and then if this matrix turns out to be positive definite, then the function is strictly convex actually. So, this is very easy now. Now, because we have a function f of x in a multi-dimension in general, we have x star value, and around that value we will be able to kind of evaluate this matrix, and once you evaluate you can take the eigenvalues of that, and then if it is a strictly positive definite, then it is a strictly convex function. The f of x is strictly convex at x star, around x star values, that is what you are talking actually. Okay. So, then if it is positive semi definite, it is only convex, it is not strictly convex. Similarly, it is negative definite, that means all eigenvalues are strictly less than 0, then it is strictly concave, and so on actually. And if there is some eigenvalues are positive, some are less than or equal to 0 like that, then it is certainly indefinite, that means you cannot have any classification actually. Now, the answer the results tells us that j of x and then gj of x, these are the two things that acts as in the Kuhn-Tucker conditions, remember that. And the results ultimately tells us that if j of x is strictly concave and gj of x is convex, then it is a maximum point, and if it is still convex only here and the jj of x is convex this time, then it is a minimum point. So, you have to see this needs to be the constraint equations needs to be always convex, and the cost function that you are talking has to be like either concave or convex actually. If you have a concave function, it leads to maximization, a convex function, it leads to minimization actually. But these are like the conditions that are necessary for sufficiency check actually. Okay. Now, it turns out that under these conditions, the Kuhn-Tucker conditions are also sufficient actually. That means, we really do not have to check too many conditions after that actually. If you apply Kuhn-Tucker conditions, arrive at certain answers based on these observations, and then you go and verify whether some of these conditions hold good actually. If they hold good, then Kuhn-Tucker conditions are also sufficient actually. So, let us see an example before we wind up. Minimize this objective function again the same quadratic cost function, and then subject to these two inequality constraints, like these two has to be, one is strictly less than 5, less than or equal to 5, x1 minus x2, and x1 minus x2 should also be greater than 0 actually. Okay. Greater than or equal to 1 basically. So, now let us see, okay. That means, you are looking for x1 minus x2 between 1 and 5 basically. This is greater than 1 and less than 5, the same thing actually. So, we are asking for solutions between 1 and 5, and you have to first split this thing into two such equations and take the negative sign of that and take all these things to the left hand side and put it in a less than equal to format. I mean that is what we have started our analysis with respect to that actually. So, all these constraint inequality constraints, I mean the whatever inequality constraint is there, all these things we need to put it in less than equal to format actually. So, we put that and then we proceed with the algebra here, and in this algebra we really do not have to talk about mu, the slack variables here, that is only the analysis and development of results basically. So, here we consider this as like an active constraint, that means equal to 0 and then talk about j bar, which is like this, lambda 1 times first constraint equal to 0 and the lambda 2 times second constraint equal to 0 actually. Okay. Then we talk about necessary conditions which tells us del j bar by del x 1 and del j bar by del x 2 0, and then it will satisfy, because remember x 1 is like lambda 2 minus lambda 1 by 2 and x 2 is negative of that, that means x 2 is equal, I mean minus of lambda 1 actually. So, these are the only, I mean all that we need to do here. Remember, if you go back to that, this set of condition tells that we need to simply analyze these two actually ultimately. So, we just do not have to consider derivative with respect to lambda j, derivative with respect to j, all that is embedded in this analysis anyway. So, we simply formulate this equation and then analyze actually. So, that is what we are doing here. Okay. So, this is with respect to x, and actually this condition tells us that x 2 is minus of x 1 and then lambda 1 times g 1, okay, g 1 is that is equal to 0, then lambda 2 times g 2 is equal to 0. So, this set of four equations will arrive at actually, 2 coming from this partial derivative being equal to 0 and 2 directly from lambda I g I equal to 0 that way. Okay. So, we have 4 variables here, x 1, x 2, lambda 1, lambda 2, and we have 4 equations. So, we can actually go ahead and solve that. And on the way we have to obviously satisfy these conditions. Remember, these are necessary conditions actually what we told here. So, it has to be, both have to be opposite sign or both have to be same sign. Okay. It cannot be partially this way, that way actually. So, that is the condition that we want to analyze here. Okay. And okay, all these conditions we will put together and then see this case by case analysis sort of thing, lambda 1 equal to 0, lambda 2 not equal to 0, and then what happens actually. So, and it turns out that this is the only feasible solution which will satisfy all the conditions actually. Otherwise, all these case 2, case 3, case 4, these are all not feasible, because it will not satisfy one of those conditions actually. Okay. So, I mean, and then they have to be satisfied with respect to this pair actually, like this has to, when this is less than equal to 0, then the corresponding lambda j has to be greater than equal to 0. So, this pair sense has to be satisfied actually, and this results does not hold good for all other case solutions actually. That means, for this case 2, case 3, case 4, something or other will fall out actually. So, this is certainly not feasible solution, but case 1 turns out to be feasible. So, and hence this is the only solution basically. So, ultimately what solution you are getting is x 1 is half and x 2 is minus half basically. Sufficiency condition we will analyze whether these are convex or not. So, we will talk j of x is x square plus x 2 square, x 1 square plus x 2 square, it is obviously strictly convex, and g 1 of x and g 2 x are also convex actually. Okay. Because g 1 of x and g 2 of x, if you see this way, these are all linear functions are certainly convex functions anyway. Okay. So, that Kuhn-Tucker conditions what you are getting are both necessary and sufficient actually. Okay. And also remember that del square j by del x square, which turns out to be this, which eigenvalue is strictly positive 2 2, that means this del square j by del x square is a positive definite matrix, and it does not depend on the value of x, and hence whatever solution we got here is actually a global solution, it is a global minimum basically. So, this is another way of kind of analyzing whether the solution is global or not actually. So, this particular thing I will probably all this I will is sufficient exposure. Okay. So, we talked about various cases, we started with a very scalar things which is okay. Let me go back to that. We started with a, see this unconstrained optimization we started in a scalar sense, then we went with the equality constraint, and then we generalized that to multiple dimension, then went to equality constraint, then inequality constraints, and a lot of numerical examples we saw, which is given overview of ideas that how do we handle optimization problems. But remember, the optimization problems are typically not that easily solvable in terms of closed form solutions. Whatever solution we are getting here nicely, these are only valid for small problems actually. So, for a big dimensional realistic problem, we certainly need numerical methods to solve these, and these are certainly not part of this course basically. But you can, if you take a optimization book, you will see a lot of numerical examples and numerical procedures actually, iterative solutions like that actually, and there are many constraints that will come, that means that many concerns actually, whether the solution, the iterative procedure will ever converge. If it converges, will it ever converge to the real solution, or it get trapped in the local minimum? All these things will be an issue as far as these conditions are, these practical difficulties are concerned. But anyway, we are not so much bothered about that. Our motivation is go towards optimal control, and we will not be so much interested in static optimization. It only gives you some sort of a flavor to appreciate what goes on in the dynamic optimization sense. So, next class I will carry on with the ideas of calculus of variation, in other words the dynamic optimization problems, and I will see how these ideas are actually useful for deriving optimal control solutions as well actually. So, this particular lecture I have taken these two references. One is this estimation and control of systems. This is a nice kind of appendix where all these conditions are discussed nicely actually. And if you are interested in lot more details about optimization theory and then associated algorithms, all that, then there are many books, and out of that probably this one book is also a good book actually. You can probably see this. With that I will conclude this lecture. Thank you.